So welcome everyone to the February novice meeting. My name is Chris Morissette. I'm the novice chair for the Houston Astronomical Society, and I think we've got a real treat for tonight. We have a guest speaker, Mr. Bill Spizzirri, and Bill is going to be describing the Milky Way galaxy and its components. He's going to explain how big the Milky Way is, where it is, and how to see it. And he'll also describe different kinds of other galaxies and how they are distributed across the universe. Bill is a retired mainframe software engineer from Chicago. He's been studying astronomy for 69 years. He has belonged to several astronomy clubs for 46 years and served in various offices, including president of an astronomy club in Chicago. His favorite astronomy activity is teaching astronomy to children and the general public. He currently lives in Katy to be near his 3 grandchildren. So with that, I'm going to turn the floor over to Mr. Spizzirri. So I'm going to stop sharing my screen, and I'm going to give Bill I'm going to make you a co-host. And in doing so, you should be able to share your screen, Bill, and we'll go from there. One thing, if you would, during Bill's talk, if you'd stay on mute, and if you have any questions, put them in the chat, and then when Bill finishes up, we'll circle back and go through the questions. So with that, I'll turn the floor over to Bill.
Okay. I'm getting there.
There you go.
You see my screen, but I want to get it into regular slideshow mode.
Right.
And, I think I did it. Now, let me just get rid of this stupid menu on the top. There we go.
Okay.
You see the big, our Milky Way galaxy?
Yes.
Okay. I can't see any of you now the way I have it, so I'm not going to press any buttons at the risk of exploding something. Thank you very much for the intro, Chris. I only have one correction. Now that it's 2025, I've been studying astronomy for 70 years. So there you go. Not important, just the trivia. Okay. Let's see. Our Milky Way galaxy. As Chris mentioned, I'm going to show you lots of stuff. I'm going to try not to talk too fast. And Chris, you let me know how we handle questions. Would it be during or after? Whatever you want to do is fine with me. I have to be in bed by midnight, but other than that, I got plenty of time for questions, okay?
Yeah, we're going to put questions in the chat, Bill, and then we'll come back.
Okay, fine. I can't see the chat now, and I don't know why. But
well,
I'll get on my way.
I'll moderate that, Bill, so no worries there.
God bless you. Thank you. As Chris mentioned, the 3 important things are, what is the Milky Way? Where is it? And how you can see it. And if you have not seen it, holy mackerel, you got a pleasure in store for you. Okay, so the Milky Way is a spiral galaxy. Here is a picture of a spiral galaxy. There's gazillions of them out there. They're all the same, and yet they're all different. You'll see lots of pictures of those tonight. So, spiral galaxy. I don't have to explain why they call it a spiral. You see it's got a bright center. All that light in the center is starlight. All the bright stuff in the spiral arms is starlight, or at least 99% of it is. Some of it is gas clouds that are glowing. We'll talk about that a little bit. And then the dark stuff looks like there's no stars there. That's actually dust in the arms of the galaxies. There's your spiral galaxy. We'll talk about all that stuff more later. Here's another one. As you can see, it's the same thing, but it's different. The shapes are a little different. The amount of dust is different. The brightness is different. Here are a bunch of spiral galaxies and infrared light taken from the new Webb telescope. That's why they look kind of orange and why they look kind of strange. But as you can see, they're all different and they're all the same at the same time. Spirals, okay? All different shapes and sizes. Now, here is our Milky Way galaxy. Now, why does it look like that? Now, if this was in person, this would be much easier, but I'm going to try to show this to you. Here is my only model of the Milky Way that I can find, okay? It's funky looking, all right? But the important thing is they say disk. With most of the stars where that's red here, it's really not red in the real Milky Way, but the redness means these are the older stars, which is in the center of our galaxy. You can see the spiral shape. The yellow stuff is stars. If you can see the blue, that's dust in our galaxy. Okay, so there's the Milky Way. All right, and it's a disk. Okay, and it's a flat disk. It's like a blueberry pancake. Okay, all right. So again, in person, this will look better. But anyway, there is our Milky Way. So, but we don't see it like this because we're inside it. Okay, it's 100 light years across, as you'll see, and our sun, our whole solar system, is just one of these yellow dots, and it's located right about over here, not in the center or all the way at the edge, but right about over here. So when we're looking at the majority of the galaxy, we're looking this way. So we don't see a disk, we see a stripe. Okay? And in this picture you see, I just realized that the only way you'd see what I'm talking about is if you're looking at my picture. I hope you guys have been able to see that. Okay. That's it. It's when you're not doing it in person, it's tricky. So the stripe that you see when you look towards the edge of the Milky Way galaxy is the stripe you see in this photograph, okay? And all the other stars that you see are just stars in the Milky Way that are closer to us, okay? But the stripe you see is the way our galaxy looks from the inside edge on, okay? All right. So here's another spiral galaxy. It's got a lot of dust. You saw some of the dust in the other pictures. Look at all this dust. Somebody's got to clean that up. I don't know who's going to clean up that mess. A lot of dust. Here's another one with called the Sombrero Galaxy because it looks like a Mexican hat, I guess. And look at the dust lanes of this one. Oh, where the heck does the dust come from? Virtually all the dust in galaxies comes from the ash of stars that exploded mostly billions of years ago. Okay, when they explode, they turn into material that isn't glowing, dust. And so that's what it looks like in a galaxy. So here is a diagram of our galaxy. Obviously, this cannot be a picture because we're, as I mentioned, we're inside it and we can't look at it from this angle, right? So there's a diagram of it. You can certainly see the spiral arms, and some of them have names, simply because of which constellation we see them in of Earth. You see it says sun over here. We'll talk more about that. You see in the center of the galaxy, as opposed to the model that I showed, the center is not spherical, but is a bar. It's elongated, so they call it a barred galaxy. So you see the spiral arms, you see some of the dark dust. As it mentions in the upper left, 200 to 300 billion stars, depending on who you talk to. It's kind of hard to count all the stars in a galaxy. And approximately 1.5 trillion solar masses. That means it has the mass of 1.5 trillions of our suns. So it's a very big object, right? So here's another picture. As I mentioned, it's 100,000 light years across. What that means is it would take light, the fastest thing in the universe, to go from one side to another. It would take 100,000 years. It's a big thing, okay? You see the red circle, that's the orbit of our sun throughout the galaxy. Yes, our entire solar system orbits the galaxy. We'll talk more about that in a second. And of course, you are here, red arrow points to where we are, about 27,000 light years from the center of the galaxy.
Excuse me. Hey, Ben.
Yes, go ahead.
Sorry to interrupt. There was some technical difficulties with the meeting. A lot of people could not get in. So you, as of the last 2 minutes, you now have about 4 times as many people here as when you started. I don't know if I don't know if it's too late. You probably don't want to start over, but I don't know. Maybe do something to catch people up. I don't know. I'll leave it to you. But
will you adjust my pay accordingly?
Sure.
Okay, I can start over. I mean, they bought tickets, so they deserve to see the whole thing. Right?
Yeah. Sorry about that, Bill. Like there were only like 7 people who heard your first 10 minutes.
Okay.
Thank you, Steve. We appreciate that.
Yeah, no problem.
Yeah, thanks for letting me know.
Sure.
I want to earn my salary. So should I continue now?
Go ahead, Bill. Yeah. Everybody.
Okay. Hello.
Anybody who shows up now was actually late.
Okay, fair enough.
Right.
Fair enough. Okay, my name is Bill Spizzirri. We're going to talk about the Milky Way. The top three things I want you to get from this is what it is, where it is, and how you can see it, especially naked eye. How you can see the galaxy naked eye, and it's incredibly beautiful. Okay, so the Milky Way is a spiral galaxy. Here's a picture of a spiral galaxy. This is not us. We can't get a picture like this. This is another galaxy. We can't get a picture like this because we're inside the Milky Way. We'll talk about that a lot more soon. But here's your typical spiral. You see the spiral arms. You see the bright center. All the bright stuff is starlight. 99% of it, there's a small amount of the light comes from glowing gas, but most of it is starlight. The dark lanes, let's see. Can you see my cursor? Yes. Okay, so the dark areas that look like there's no stars there, that's actually dust in the galaxy. We'll talk about that some more. Here's another spiral galaxy. Of course, it's different, but it's the same thing. A bright center, spiral arms, very bright, dark dust lanes, right? Here's a whole bunch of spiral galaxies, photographs taken by the New Webb telescope, which photographs in infrared. That's looking at heat, so these images look a little strange. But as you can see, you know, there's lots of spirals out there. They're all the same. They're all different. Here's what our Milky Way looks like. Well, you don't see a spiral here. Let me ask you this. Can you folks see in my picture this thing I'm holding up in front of me?
Yeah.
Yes. Okay, good. So this is my kind of funky looking model of the Milky Way galaxy. It's a weird one because it's the only one you could buy. Bought it 30 years ago. Okay, so you see the spiral shape. The yellow is all starlight. The blue, if you can see it, is dust in our galaxy, spiral arms. The red stuff really isn't red if you look at our galaxy. The red indicates that there's older stars in the center. Okay, and it's a big disk. And it's a flat disk like you saw from some of the photographs, okay? And but we cannot see the disk because we're inside the disk. Our entire solar system is just one of these yellow dots, and it's right about over here, okay? And we're going to talk more about that. I just wanted to tell you that's where we are. This is what the Milky Way, how it's shaped, more or less, and that's where we are in it. So when you look out naked eye up at the sky, you're seeing the galaxy like this. You're seeing a stripe, which is what you see in this picture over here, okay? So you see the stripe because we're looking towards the center of this galaxy. You can see the bright starlight. You can see the dark dust lanes. And all these other stars are just stars in the Milky Way that are closer to us. Sorry for the repeat for everyone. Here's one, another spiral galaxy. Again, they're all different. Look at the dust lanes in this thing. Here's another spiral galaxy with dust lanes. Okay, very prominent. This is called the Sombrero Galaxy, a beautiful spiral galaxy. And by the way, all the dust has basically one source, and that is it is the ash, the leftover material from stars that have been exploding, mostly large stars, over billions of years. Okay, so it's dust. It's cold, so it doesn't glow, so it looks the way you see it. Okay, dust. So here's a diagram of the Milky Way. You can see the spiral arms. The spiral arms have names based on what constellation we have to look through to see that spiral arm. And as you can see down here, the sun is located over here. You can also see the center of the galaxy, as opposed to the model that I showed you. The center is not round, but it's elongated. It's like an oval, and so they call this a barred spiral galaxy. As it says in the upper left, 2 to 300 billion stars, depending on who you ask, it's hard to measure, and approximately 1.5, that's not how you spell trillions, by the way. Although I could say 1.5 trillion solar masses, about the same thing. 1.5 trillion solar masses means it has the mass 1.5 trillion times the mass of our sun in the entire spiral galaxy, okay? So it's big. It's 100,000 light years across. That means if you shine a flashlight all the way from the left-hand edge towards the right-hand edge, it would take that light, if it actually made it there, it would take 100,000 years to get there. And light is the fastest thing in the universe.
but the galaxy is big, so that's how big it is. The red circle is the sun's orbit. Okay, yes, the sun and the entire solar system orbits the galaxy, and where we are more or less right now is over here. Okay, looking towards the center of the galaxy. All right, that's all I can say here. Now, here's another picture where we left off before. Shows more or less the same picture, but because Earth has seasons, and the seasons are show well in the sky. In the winter, we'll see Orion. In the summer, we'll see other constellations because the Earth goes around the sun. So that's why we have our seasons. And so in the summer, we're looking towards the center of the galaxy. That's why that picture I showed you earlier, where the galaxy is very prominent across the sky, we're looking right towards the center of the galaxy. In the winter, when we're on the other side of the sun, we're looking in this direction where the blue arrows are. And so we can still see the Milky Way, but the view isn't as spectacular and it's a little more harder to see. So as it says here on the left, the best view is in the summer. But if you're going to go out there and look for it, get in the dark sky and take a look. So as I mentioned, you see they call it a central bar. Oh, let me get rid of this stupid menu here. We call it a central bar. The galaxy rotates. It's a rotating object at 500,000 miles an hour, 500,000 miles per hour, okay? It spins once in approximately 212 million years. So fast, but slow for one orbit. Now, there's been a recent picture. I don't know if you guys seen the recent picture of the Milky Way. It's very descriptive. Guess what? When I got rid of those menus, oh, wait, here we go. There's the picture. This is the new picture that I was talking about, which shows the central bar in our Milky Way galaxy. Okay? Yeah, there's not too many galactic jokes. That's about it. Okay? That's all there is to it. I love those candy bars, so I couldn't resist. All right, so I showed you that picture earlier. When you look at the galaxy from our point of view, you see a stripe. So here, horizontally from left to right is a close-up of the stripe of our galaxy. You can see the bright starlight. You can see the dark dust plains. And this is what it looks like in visible light. And really, if you get in the dark sky, you will see an image very similar to this, depending on how dark the sky is, especially if it's in the summer. This, by the way, over here is pretty much toward the center of the galaxy. So we know what it is now. I already told you, that's all starlight, right? But it was a big deal when this Italian fellow, Galileo, first pointed his telescope at the sky, first pointed it at the Milky Way. And, you know, we called it the Milky Way back then. We still do, because in the, the legendary stuff, what do you call it? Anyway, in the legends, the Milky Way looked like milk from the breast of the goddess Venus. And then Galileo looked at it and he said, he said, Mamma mia, that's Italian in case you don't know. It's all clusters of stars. Now, that's not news for us today, but that was a big deal back in the 1600s, okay? So he thought it was a big deal. So he took his telescope to this tower in Venice. I went out there, took the elevator, and he shined his telescope out of those black oval windows on top of the tower in Venice in St. Mark's Square. And he showed it to all the rich guys to sell the telescopes to them. And then in the bottom of the tower is this plaque, which if you can't read the Italian, it says here, Galileo with his telescope in 1609 widened the horizons of man in the fourth centenary. The fourth centenary refers to 400 years after some event, I don't remember what. But anyway, it's on the wall in the back of the gift shop, so most people don't see it, but I got to go up there where he did that. So, you know what the galaxy is shaped like now, and you know what it looks like now, more or less. So a guy took an ordinary visible light camera and took a picture of a small piece of the Milky Way. And then he moved his camera over and took a picture of the next piece. And then he moved his camera and took a picture of the next piece, and the next piece, and the next piece. And then he kept taking, he had to go all the way around the world. and took pictures of the entire galaxy with an ordinary visible light with an ordinary visible light camera, and this is what he saw. So this is how the Milky Way looks from the Earth in ordinary visible light. Obviously, you can see the starlight. You can also see that, oh my God, we have a lot of dust in the galaxy obscuring a lot of the starlight. All right. But that's just the way it looks from Earth in visible light. By the way, these two little blobs over here are tiny dwarf galaxies that orbit the Milky Way, called the Large and the Small Magellanic Clouds. They were first recorded by Magellan as he went in the southern hemisphere. You got to be in the southern hemisphere to see the Magellanic Clouds. Okay, so that's what it looks like from the Earth. Now, if you take a picture in infrared, kind of like the Webb telescope does nowadays, what a big difference. There's visible light, there's infrared. It's the same galaxy, trust me, and yet you see the center section much, much better, and you still see some dust, but the thing is that you don't see as much dust because the infrared light goes to a large extent right through the dust. So we can see the starlight much better when we look at the galaxy in infrared. Just one of the many reasons why Webb is an infrared telescope. So we see our galaxy like this, okay? And we look out in the universe and we see other galaxies, other spiral objects like this. And about 120 years ago, we thought these were so-called spiral nebulae in the Milky Way. And but after a while, we learned that those were other galaxies. And when we saw them and we learned that they were other galaxies, we said, okay, that's what we look like to somebody in another galaxy. All right. Here's the same thing in the infrared with the more powerful telescope as seen from Earth. You see the dust, you see the central bulge, and then there's the Magellanic Clouds there in the corner. Okay. Now, another thing we have in our galaxy, and this is true in all galaxies, is we have clouds of dust and gas. And some of these clouds are where stars are forming, and some of these clouds are the result of stars that died and exploded. In the upper left-hand corner, you have a famous cloud called the Orion Nebula, in the constellation of Orion. In nice conditions, you can see it's a foggy little patch, kind of a naked eye. And here there's, I think, dozens of stars that are forming, brand new stars that are just forming. And this is where stars form, in clouds of dust and gas. Okay, that's a whole other presentation, but we'll just suffice to say that. Now, these other three are the results of stars that died. The two on the right are the result of stars that, not too big stars, kind of medium, small to medium stars, and they ran out of fuel. So when they do, they go through an evolutionary process which involves throwing off their material out into space. Both the one that looks like an hourglass and the circular one. That's it. Medium-sized stars that throw their material out into space. The one on the lower left is the remnant of a supernova, where our large stars exploded in a very violent explosion, the most violent events perhaps in the universe. And so it's throwing all its dust and gas out into space. So just suffice to say, the Milky Way has a whole bunch of these gas and dust clouds all over it. Again, some where stars are forming, some where stars died. Now, you have these two on the right that are very different shapes. Why do they have such different shapes? So let's say there is one pair that exploded and it formed the hourglass shape, as it shows in the lower diagram. Well, if the eye was up here where my cursor is pointing and you were looking down at it, you could see the hourglass going out, shall we say, to the left and the right, as this picture shows from the Hubble telescope. But if your eye was located over here and you were looking this way, you cannot discern the hourglass shape. Instead, you see something like this helix nebula that you see in this photograph, okay? So I just wanted to explain why these clouds look so strange. Okay, so here's the Milky Way galaxy. And you know how it's shaped and what it's made out of. Well, here's something I didn't tell you about. Along with the spiral shape that from Earth we see edge on, as in this picture, it also has a huge halo of gas. When I say huge, 90 billion solar masses of just gas, not stars or planets, just cold gas, that did not become part of our galaxy. Perhaps it was the gas cloud that our galaxy evolved from. Don't know for sure. Probably, though, I guess I would say. It's about 200,000 light years in diameter. Remember, our Milky Way was 100,000 light years in diameter. And notice it's not a perfectly circle shape, which you might expect. And it's believed that this warped ovoid elliptical shape is due to dark matter. Again, a whole nother presentation, but it's dark matter is stuff that has a gravitational field and it can warp the shape of stuff in space. So the Milky Way has this large halo of gas. That's a whole nother presentation. Now, here is a big galaxy that's close by called the Andromeda Galaxy. Why? Because that's the constellation you will see the Andromeda Galaxy in. It's very, very close. It's very close, only 2 billion miles away. Okay, and it's bigger than the Milky Way. But as you can see, maybe you could tell it's. If I told you it was the Milky Way, you'd be hard pressed to be able to argue with me, except you would know that there's no way we could get a picture of the Milky Way like this because we're inside it. Anyway, it's bigger than us, and it's only 2 billion miles away, such that if you go into dark skies and you know exactly where to look, you can see it naked eye as a fuzzy gray patch in the sky. And if on your outstretched arm, you can cover it with your thumbnail, but you'd be able to see this object that's 2 billion miles away with your naked eye. So that means the light from Andromeda Galaxy took 2 billion years to get to the retina of your eye, okay? So this is the big galaxy that's close to us, all right? And Andromeda Galaxy, if you haven't guessed already, also has a huge halo of gas around it, 2 million light years across. 3 times, to picture this in the sky, if you could see it naked eye, as in this picture, 3 times the width of the Big Dipper. So in our sky, it would be a huge object. But if you could see it, it obviously would be very dim. Well, it's up there and we can't see it, so it's extremely dim, okay? So if you could see it and you took a picture, here's our Milky Way here, and this is how big the halo of Andromeda would look in our sky. Absolutely huge. And astronomers would be studying it for centuries. But that just shows you it's big and it's close. Another thing that Milky Way galaxy has, and many other galaxies have these too, are so-called globular clusters. Okay, they're just these round, they're spherical groups of stars, up to a couple million stars. All right, and they're very beautiful in the telescope. I don't think you can really see them naked eye. I don't think you can, but in telescopes, they look like jewel boxes. They're absolutely beautiful. And if you get your hands on a telescope, I suggest you give it a try. They're very beautiful. And the Milky Way has a lot of them. As a matter of fact, there's a whole bunch of them around the Milky Way. And about 100 years ago, they figured out where the center of the Milky Way is by looking at the globular clusters, figuring out their orbits, assuming they were orbiting the center of the galaxy. They could then pinpoint the center of the galaxy by looking at the orbits of the globular clusters. So as you can see in this picture, we got a whole bunch of them. I get varying numbers from 50 to 150 of globular clusters. So here's a diagram of the Milky Way, and you can see the globular clusters are all around us. There's many of them, some of them very bright. Again, they're great in telescopes. Here's another thing that our galaxy has. You've probably heard about it, a supermassive black hole. It's an object at the center of our galaxy. It's called the black hole because it's so massive, as you can see in the upper left, 4 million solar masses, 4 million times the mass of our sun. So its gravitational field is super strong. Its gravitational field is so strong, nothing can escape it, not even light, which is why they call it a black hole. It's approximately 1 million miles in diameter, depending on how you want to measure it. There's different ways of measuring a black hole, but it's suffice to say it's very big. So that 1 million miles is approximately the size of the orbit of Mercury. Okay, so there is the spiral galaxy. That's supposed to be us. You can see the black hole, and it's shooting material in both directions. So light can't escape it. So how do we know we had a black hole in the center? Well, For 26 years, people have been taking pictures of the center of our galaxy, and they see that there's several stars in this picture here, 4 stars, and the blue circles are the orbits of the stars. This is a video I'm going to show you. And so we watch how these stars orbit. And by the way, they're orbiting this area over here, and we saw nothing over there. Yet they're still orbiting it, right? And so I'll start the video now, and you'll watch this star called S2 and watch it in its orbit, and we'll see what happens. Okay, so here's S2. It's orbiting nothing, and it's going very slowly right now because it's kind of far away from nothing. See, we call it S2. And they cheat. They show you where the black hole is. And now it's because of gravity, it's in orbit around the black hole. It's moving towards it, and it's moving faster and faster and faster. And then it goes really fast, and it goes back out again, and it slows down. It slows down because when you're orbiting an object, the further you are away, the slower you go. And when you're close to it, the faster you go. That's why Pluto takes 250 years to orbit the sun, and Mercury goes around much, much quicker. Okay. And as you can see, that's what the S2 did. It was close, it was fast, and when it's far, it's slow. Now, since we could see these objects orbiting nothing, and we could see the speeds at which they did it, we could use ordinary Newtonian gravitation mathematics to figure out the mass of the object that they're orbiting, and that's how we know 4 million solar masses for our giant black hole. Here's another video. It shows you there's a whole bunch of stuff orbiting the black hole. All right, and it's kind of chaotic, but there you go. Look at all the orbits. There's all kinds of stuff orbiting the center of our galaxy because of the strong gravitational field of the black hole. I don't think you need to watch that all day. This is a diagram. I hate to give you a diagram, but here's our buddy S2. You saw that orbit, okay? Oh, by the way, I don't know if you noticed it said there 2 light years across over here for the orbit of S2. Here's the size of the orbit of Neptune, which is basically the size of our solar system. It's smaller than all of the orbits of these stars. Why do these stars have such large orbits? Because the gravity of the black hole is so doggone strong, okay? So it's a crazy thing. Black holes, 50 years ago, nobody believed they were there, and now we see them at virtually every big galaxy out there has a supermassive black hole in the center of it. Now, our galaxy, all the ones we've been looking at were spiral galaxies. That's not the only kind of galaxy out there. There's also galaxies like this called elliptical galaxies, okay? And they don't have a lot of new stars forming, whereas, I forgot to mention this, but spiral galaxies have lots of star-forming regions. Okay, elliptical galaxies, very few, and they're very older stars, okay? And as you can see, there's no dust lanes, or sometimes they have them, but very few, and some of them have none. And they call it elliptical because they're like big balls of stars, and they're frequently very large. And I remember the day that I learned back in about 1974 or 5, when the theory came out that all the ellipticals formed by the collisions of spiral galaxies. So you have our galaxy with hundreds of billions of stars colliding with another galaxy of hundreds of billions of stars. And it's what they scientifically refer to as a mess, okay? The gravity situation, the mass situation of all those galaxies colliding with each other. First of all, one of the things that happens, as you can see, is they lose their spiral shape. It's all messed up, and the spiral shape is gone, and you end up with an elliptical galaxy. So there's lots of those out there, and they're called elliptical galaxies. Okay, we don't live in one. So in the lower left-hand corner, you see that giant galaxy, the Milky Way that I told you about. And then the Andromeda. Now, I don't know if these 2 pictures are accurate, but I know Andromeda is bigger than the Milky Way. I think this might be a slight exaggeration. But then even bigger than Andromeda is an elliptical galaxy called M87. It's a big one. No, I don't remember how many solar masses it is, but it's way more than the Milky Way and Andromeda. And then here is a galaxy with the clever poetic name of IC 1101, which has about 100 trillion solar masses. Okay, this is, I believe, the largest galaxy kind of measured from side to side that we know about, except for this guy here, and I'm not sure how to pronounce it, Alcyonius, maybe. I don't know. You can now. Here's the galaxy, this tiny little dot, and it's a radio galaxy, so it's putting out radio waves a lot, right? And since it has a magnetic field, the radio waves shoot out from the north and south poles from the galaxy. Doesn't look like much here, okay? But the radio waves hit the intergalactic medium where there's gas out there. Remember I told you how gas halos around galaxies? And when those radio waves hit that gas, it causes the gas to glow. So this is really all part of, if you will, this galaxy here. The central black hole, which is causing these radio waves, 400 million solar masses, 100 times the one in our galaxy. This is all 16 million light years long, 240 billion solar mass. It's big, okay? So I'm just trying to show you this is a big one. Now, the saying goes, if you want to find a galaxy, look where there's other galaxies, because galaxies frequently hang out in clusters. Okay, why? Maybe they formed that way, but almost certainly some of them did. But also their gravity tends to make them attracted to each other. So we see lots of galactic clusters out there. As you can see here, we have both spirals and an elliptical, right? Here's another picture. Many galaxies in a cluster. Now they look like they're close, but there's probably millions of light years in between them. But in a photograph, it's definitely a galactic cluster. Now, the Milky Way galaxy lives in a galactic cluster, a kind of a small group called a local group. And it has 30 to 50 galaxies in the local group, depending on who you ask and how you want to count them. So the Milky Way is right over here. Okay, here's Andromeda, our buddy, and the rest of them are, you can't even see it in this picture. They just have dots to indicate where they are. But this is the local group. Some of it was probably, like I said, we were formed this way, and some of it was just attracted by gravity to get close to us, the local group. So here is something that happens when galaxies are in clusters and they get close to each other. It's nothing but trouble. The gravity of this guy and the gravity of that guy is just attracting the two galaxies towards each other. And I don't know if the people in these galaxies know it, but they're in for some fireworks, okay? Galaxies collide a lot. One, because they're in clusters, so they're close to each other, and two, they have so much mass, their gravitational field attracts them towards each other. There is a typical example. Two spiral galaxies, or what were spiral galaxies, and this galaxy, the upper left, its gravitational field is pulling entire star systems, stellar material, and gas, and you can see the dust is being attracted from this galaxy towards that galaxy over there. So when they get close to each other, this is what happens, okay? Look at this. I think this used to be a spiral galaxy based on the dust lanes. And this is definitely an elliptical galaxy in the lower left, but the large gravitational field of this elliptical is just totally distorting the shape of that spiral galaxy. What causes that? It's all gravity. Okay, that's really the force that makes almost everything happen in the universe. But so that's what happens. Here is another large spiral pulling material off a smaller spiral, but it's not the large spiral's fault, it's the small spiral's fault for getting that close. You get that close, that's what happens. Somebody's going to steal all your material. And of course, when that material hits this spiral, I didn't mention that, it's probably going to cause lots of star formation, because that's how stars form. Now, remember I told you the Andromeda Galaxy is close. You can see it in dark sky, only 2.5 billion miles. There's the Andromeda. Well, it's so close that we're getting in trouble with it. Okay, we're the Milky Way galaxy on the bottom is moving towards the Andromeda galaxy at 133,000 miles per hour. Why? Take a guess. Gravity. The extreme gravity of the Milky Way and the extreme gravity of Andromeda are attracting the two galaxies towards each other. But don't worry, you can still buy green bananas. You'll be able to use them. It's going to be 3 or 4 billion years before, quote, we see anything. Okay. And there's our buddy I mentioned earlier, Triangulum M33. You're going to see him again soon. So we're moving toward them. And in 3 billion years, give or take, don't quote me on that, we'll still see the Milky Way, I guess, I think. The big stripe, remember, we see our galaxy as a stripe in the sky because we're inside it. So the Milky Way is still like this, but the Andromeda will be coming close. Look at this. When the Andromeda galaxy is big enough to be half of our sky, we'll see it, doggone it, if we're still here in 3 billion years. It remains to be seen. And this is what it'll look like, more or less, okay? It'll be darn interesting. If this is inaccurate, no matter what it is, it'll be interesting. Okay, so see it now while you can, okay? I'm not telling you to do it, just a guideline. And as a matter of fact, that collision has already begun because the halo of the Milky Way galaxy, we know that it's there, we know how big it is, has already started to merge with the halo of the Andromeda galaxy, neither of which we can see in the sky, except with very special telescopes and cameras, but they're starting to combine. So, you know, it won't change what you do this weekend, but just to tell you that that's happening. So, collision. Here's a short video that shows you the Milky Way and the Andromeda, and it's speeded up. And look in the lower right-hand corner how the time is speeding up. We're already through 500 million years. Milky Way is spinning like crazy because the time is speeded up, okay? The camera angle is changing now. And here's Andromeda, okay? There's our buddy, the Triangulum galaxy. It's just called that because you see it in the constellation Triangulum. And now these two big guys, their gravity has attracted them to each other, okay? The camera angle is changing. And we're speeding up just like the Star S2 did, and zoom, we go right through each other. Why through each other? Because galaxies are mostly empty space. There's billions of stars, but there's a lot of space in between them. So we go right through each other, and then we go right through each other again and again, and guess what we form? An elliptical galaxy. And there's Triangulum, who does not participate in this collision. Maybe he wants to, I don't know. Wants to play with the big guys. But somebody has mentioned that, I don't know. So you can think of a name of what we'd call this elliptical galaxy, but that's what the astrophysics that we have today tells us is going to happen 3 or 4 billion years from now. Okay. Now, you might say, collisions, that's crazy. Well, I hate to tell you, I don't hate to tell you, but I'm going to tell you, that's already happened with our galaxy. Our galaxy is a cannibal, okay? We have studied the stars, especially on our side of the galaxy. You know, we're down over here. So we can see what's going on this side of the galaxy pretty good. And we see that there are thousands, maybe millions of stars, these green ones. They don't look green. They're just colored green so you can see them. They used to be in a dwarf galaxy that got too close to the Milky Way. And we ate it up and we wrecked it, tore it to pieces. And we could tell that they used to be one dwarf galaxy because of their orbits. They're all orbiting together, okay? And so they used to be in a dwarf galaxy that got too close to the Milky Way. And you can apologize to it if you want, but that's just the way it goes. Now, many of you may recognize this. This is our buddy, the Hubble telescope, launched 30 years ago or something like that. I forget. It started working about 31 years ago. Fantastic instrument. It's in orbit around Earth. It's a big, fantastic telescope. It photographs things in regular visible light, more or less. Okay? And the guy who was in charge of it said, I got a good idea. Let's take a picture of space where there's nothing. And everybody told him, oh, come on, that's stupid. And the guy said, no, we're going to do it. You know why? I'm the boss. So we point the Hubble towards a space where they see nothing. And they did this 4 times. You can see the dates on the left. Okay. So where are they going to point it? Well, they find this little spot that happened to be not always next to the moon, but it happened to be. I showed you in this picture. The XDF means extreme deep field. Okay. That means the photograph that Hubble took was a piece of space this big next to the full moon. Now think of how the full moon looks. You can cover the full moon with your thumbnail, I think, in a full moon. And this is where bigger people say this piece of space is the size of looking through space through a soda straw. Think about that. That tiny little piece of space, as you would see through a soda straw. Hubble took that image. It took several days, a long exposure time, and this is what it saw. In a piece of space where we saw nothing otherwise. We saw 10,000 galaxies in that tiny little piece of space. That was in 2014. Okay, it was a revelation, that's for sure. Now, this over here is a star in the Milky Way, and I think somewhere over here is another star in the Milky Way, but every single bright spot you see in this picture, except for those 2, are galaxies. Obviously, some closer, some further, some bigger, some farther, some spirals, some ellipticals, 10,000 galaxies in the tiny little piece of sky. Now, as I mentioned, they did that 4 times. Every time they did it in a different piece of space, they saw the same thing. So they kind of increased our estimate of the number of galaxies in the universe that we can see. A trillion, maybe a trillion galaxies, maybe more, who knows. Then the Webb telescope did it in 2022. It took 10 days of imaging, 15 times the size of the Hubble image, and this is in infrared, correct, which is heat, and 9 different infrared wavelengths, right? And what did it see? 245,000 galaxies. Again, a tiny little piece of space, 15 times the size of Hubble, but Hubble's was not very big. And so we're seeing these dimmest dots that you can see here, if you can barely see them, are less than 600 million years after the Big Bang. So we're really seeing back in time. Why do we see back in time? Because the light from billions of years ago takes that long to get to our camera, okay? And so there's a lot of galaxies out there. Pick a number. So you see there's a lot of galaxies out there, and you see the galaxies form in clusters, okay? Here is an image made. This is not a photograph, obviously, but it's a computer-generated image of all the galactic clusters, maybe not all of them, and a whole bunch of them that we can see, that we have identified and located and kind of know what they're shaped like. And we put them in a big 3D image, okay? Now, our local group, remember that the 50 galaxies close to the Milky Way and Andromeda is just a dot over here. Every dot you see in here is not a star and it's not a galaxy, it's clusters of galaxies, okay? So figure at least 100 galactic clusters, okay? And this is approximately 10 billion light years across. It's a big chunk of the universe, the visible universe, okay? And as you can see, a lot of galaxies in a lot of clusters are all over the place, all right? And so, when we discovered that our Milky Way was 100,000 light years across, we went nuts because of how big it was, right? Well, look at this. Someone once said the universe isn't stranger than you think, it's stranger than you can possibly imagine, okay? And then we did all these, we sent out spacecraft that, like Gaia, that take images and measure the location, the brightness, and the speed of just billions of stars all over the universe outside of our galaxy. And here's another image of galactic clusters, and we can see that the galactic clusters aren't just randomly scattered. They're in these lines with big voids in between them, okay? This is the family portrait of the universe, right? the whole universe looks like this. They call it the cosmic web because it looks like a spider web, I guess. Okay. So that's what our universe looks like. So take a deep breath. I'm just about done. Okay. So here's that image of what our galaxy looks like in regular visible light. Maybe you could say naked eye, a little bit better than naked eye because it's taken with a camera, especially in the summer when the Milky Way starts at the horizon, goes all the way to the zenith, up straight up, and then all the way to the other horizon. What a view that is! You see the stars, you see the dust lanes. It's a tremendous view. Okay, now here's the last thing I'm going to show you. Oh, this is right. Yeah, no, this is not the last thing. This is just a picture that shows you an intrepid astronomer with his telescope seeing the Milky Way. Again, all these other stars are in the Milky Way. They're just closer to us. This is a really great view. He's in really dark sky, right? And here is a video. I'll tell you what it is. The last thing I'm going to show you is a guy went to South America in the desert where there's no clouds, for instance. And he put a tripod and put an ordinary camera on his tripod and pointed it up at the sky. And then it's a video camera, and he left it going for a couple of days. So this is about a 48-hour video of the sky that you can see the Milky Way. Cut off the sound. Okay, so there you see the sunset, the shadows, and it's nighttime. And there's the Milky Way. Wow, it's spinning. Why is it spinning? It's not spinning. The Earth is turning. Where the sun rises and sets in the west, everything in the sky does the same thing. There's the Milky Way. There's the small and large Major Cloud because he's in the southern hemisphere. Okay, and the sun comes up, sky brightens, the shadows disappear. Right? Yes, they do. Okay, you see the shadows getting shorter. Okay, and now it's about 12 noon. Okay, he keeps the camera going. Most of it's sitting there eating and drinking. There's the shadow of the camera. The sun goes down, and there's the Milky Way again. So, boy, it happened 2 nights in a row. What a lucky guy. That's just the way it does it every night. Okay? So, that gives you an idea. If you get in a dark sky, this is how fantastic the sight is. How far do you have to go to get to the Milky Way? Not at all. You're in it. Okay? That's what it looks like. That's where it is. That's how you can see it. So, I would say thank you very much for those of you who are awake. If you're with somebody, just elbow them on the gut and the ribs to wake them up. Thank you very much for your attention. Oh, there's my email. If you want to send me any questions, because I can get very confusing, please send me a question. It'd be my pleasure to answer them. And again, I got to be in bed by midnight, but I'm ready to take questions if you would like.
All right. Well, Bill, thanks. That was really
Yeah,
cool.
I can't hear anything, which means
Can you
I have
hear
to turn
me?
on my microphone, so I have to stop sharing.
Okay.
I think to turn on my microphone.
All right. Can you hear me now?
Wait, my microphone says it's on. Can you hear me?
I can hear you.
Oh, you can. Oh, that's right. I shut the sound off.
Oh.
That's twice in one night, Chris.
Can you hear me now?
Yes, I can.
All
Sorry.
right. Great. Hey, great presentation, Bill. Really appreciate that. And to the people that came in late, my apologies. I don't know why the meeting was locked, but I will find out why and not make that mistake again. I did send out a message in the chat for people to ask questions in the chat, and we do have one from Josh Dubach. Josh, if you'd come off mute and ask your question, that would be wonderful.
Yeah, I was just wondering, do all spiral galaxies have black holes in the center?
Good, excellent question. Man, 20 years ago, that was like a huge question in astrophysics. And we've looked around, and every large galaxy that we see, not just spirals, but ellipticals too, supermassive black hole in the center. I think what I've heard is if you're a dwarf galaxy, a tiny little percentage of the Milky Way, there's frequently not a supermassive black hole in the center. But for the most part, if you're a run-of-the-mill big galaxy, you got a supermassive black hole in the center. So they're saying, why is that? Does the black hole caused the creation of a galaxy, or is a black hole the normal outcome of the evolution of a galaxy? Okay, there is in Sweden a Nobel Prize on a shelf waiting for you if you can answer that question. Wait a minute, did they give out Nobel Prizes for astronomy? I don't think they do.
They do in physics, and
Okay, you got a physics one.
astronomers will take the lion's share of those, or will take.
Yeah, don't be insulted if you get a physics one. It's still an astronomy thing, right?
Yeah.
I'll start working on it. Thank you.
But if you want them, go for it.
All right. So thank you, Josh. I'm going to go ahead, Bill. I've got a couple of questions on my mind, and then I'll open the floor up. So you showed the cosmic web, and those, if I understood you right, were really collections of galaxies that are spread out or form what we would call filaments. I've heard walls is another formation. So that really what we're looking at is when we talk about the cosmic web, is we're talking about really just gargantuan collections of galaxies. Is that, do I have that right?
Billions of light years across. It's all galaxies. Gargantuan is as good a word as any. It might even fall short of the size of this object we're talking about here, but I think the short answer is absolutely yes.
Okay. And then the other question, you mentioned that Andromeda and the Milky Way are on a collision course. We've got the large and small Magellanic Clouds, which I think are dwarf galaxies, if I heard you right. Are we on a collision course with those two galaxies?
Oh, I don't think so. I've heard they're orbiting the Milky Way. Now, we've only been watching them for a couple of hundred years, although I am certain that the astrophysics guys have plotted their orbits of the two Magellanic Clouds around the Milky Way very carefully and precisely. I've never heard anyone say that they're on a collision course with the Milky Way. It's like we're headed for a concrete pillar in our car, and someone said, "Oh, gee, a butterfly just hit the windshield." Well, we're really not worried about that so much. You know what I mean? We're headed towards Andromeda, and I've never heard anyone measure or be concerned about us running into the small and large Magellanic Clouds.
Gotcha. Okay, so with that, I don't see any more questions in the chat, so let me just open it up to the floor. If anybody has a question for Bill, just come off of mute, and we'll go ahead and ask your question.
Bill, you mentioned that dark matter would be a whole nother talk. I'm wondering, we find evidence of dark matter in other galaxies. Is there any observations about our own galaxy that suggests dark matter?
Oh, I would say indeed yes. We see it all over the Milky Way, controlling the movement of stuff, controlling the movement of nebulae, controlling the movement of star systems, and controlling other galaxies. Well, that's outside the Milky Way. But yes, we see it in the Milky Way, absolutely, positively. And we see it in intergalactic space also.
Thank you.
You're welcome.
Any other questions for Bill? Okay, I'm going to do my auctioneer imitation. I'm going to say going once, going twice. All right, we're going to close the floor. Again, Bill, wonderful presentation.
Thank you thank you.
Appreciate it. And again, to those folks that got in late, my sincere apologies, and I commit to do better next time.
And I pressed the wrong button, but is there anybody, I had my email address on that final screen. Does anybody need my email address? Well, you know what? I don't know how long we're going to be here, but I'll put it in the chat.
Yeah. I'll leave things open for a second, and people can get your.
Spizzirri77@gmail.com. There, it's in the chat. So,
all right. So there's Bill's email address if you want to grab that and have any follow-up questions. And with that, thank you for attending tonight's meeting, and I wish you all. Oh, one thing I forgot. I'm remiss in this. We do have. I'm going to share my screen now, if I can. Yeah, here we go. Just one quick um, announcement for tomorrow. We are going to have our general talk on. There's old Bill. And we have a general talk tomorrow that starts at 7 o'clock. And the title of this is What Astronomers Need to Know About Nothing by Don Selly. And that's a tongue in cheek way of talking about or introducing the topic of dark matter. So if you can, please join us for tomorrow and to hear Don's talk. And it would probably be a good complement to what we heard tonight from Bill. So with that, I bid you all adieu. And again, thank you for
Hey, Chris.
Yes.
Just one moment.
Yeah.
Someone, Philip S., just put something in the chat, and I have to thank you, Philip, for this. Oh no, not Philip. Right. S. He says, per Google, which we know cannot be wrong, based on current models, the Large Magellanic Cloud will collide with the Milky Way in 2 billion years. So eat well and exercise, and maybe you can see that. And then M31, that's another name for the Andromeda Galaxy, which I didn't mention, 4 billion years with the Milky Way. So there's something to look forward to.
And Joyce, did you have a question?
Yes, I just wanted to, I saw Josh here, and I just wanted to invite everyone to Memorial Park on the 15th of this month. There are quite a lot of novices there at the park, so you will not be alone if you come on out. We're all learning together. And Bill, you're going to be at are you going to be at the Katy site the week after?
You mean the John Paul landing?
Yes.
You're ahead of me. I'd have to look at my calendar, but they gave me dates. There's published dates.
Okay.
And guess what? I'm going to be giving the Milky Way presentation.
Okay.
So you are welcome to come. However, you might see some of the same stuff. Excuse me, all of the same stuff.
Repetition is how we learn. So if you'd like to go into, that's right. So if you'd like to go into town, join us at Memorial Park, and we can learn together, and it's a lot of fun. And if you're further out, then definitely hang out with Bill, and it should be a good night. So
and by the way, when I'm at John Paul Landing, if the sky is clear, they have a really nice telescope outside too, with a guy who knows how to run it. So you'll have that at the same night.
All right. Well, thanks, Joyce. Appreciate that piece of information. And Pradeep, thank you for the information on the Large Magellanic Cloud. And with that, unless anybody has anything else that they want to comment or discuss or ask, I think we're finished with the meeting tonight. So again, thank you all for attending. I appreciate it.
So long, everybody.